research focuses not only on one, but on two research programs. On the one hand, she's cooling trapped molecules to study the interplay of quantum state and the motion of molecules in chemical reactions. And she's looking at high-resolution spectroscopy of complex molecules with her experimental techniques. But at the same time, she's an expert in science lab education, investigating how students learn the skills they need in a physics lab and putting those things into practice by making suggestions to improve classroom experiences in lab courses. So she's basically asking questions like, how do chemical bonds form, but also questions of the type, how do students learn experimental physics skills? And I think these are really interesting questions, and perhaps you could even consider both of them to be really of fundamental importance to physics. Her efforts have been recognized by a number of awards and honors, like a Young Investigator Award by the Air Force Office of Scientific Research, Career Award by the NSF. She's been selected as a Fellow of the American Physical Society. She's received also recognition for her educational research, like an APS Wolf-Reichert Award for advanced laboratory instruction. The citation is for systematic and scholarly transformation of advanced laboratories in physics for building leading assessment tools of laboratories and for national service, advancing our advanced laboratory educational community. So indeed, this is very interdisciplinary work that we will hear about. It's an interplay of physics and chemistry, but also her other work at the interface of physics and social science. And finally, let me point out something which I think might be of interest to the audience here, that Professor Lewandowski has also investigated how students can be best prepared to work for companies in the field of quantum science. And she's also asking questions like how to make the quantum physics workforce more inclusive. And so in case you want to have any questions about that, I'm sure maybe you can also ask them. So but without further much ado, let's start the talk, watching chemical reactions happen one molecule at a time.
Awesome. Thank you so much for the kind introduction. I'm really excited to get to talk to you all today about the work that we're doing here in Boulder. And so as I said, I'm an atomic physicist by training. So why bother studying gas phase molecules? They are a bit messier, I will admit, and sometimes I long for the days of atoms. But they're really a lot of power that comes from studying molecules. In fact, they're much more interesting than atoms in a lot of ways, right? They can rotate, they can vibrate, really interesting. They can have dipole moments where you can grab onto the molecules with external electric fields and really begin to control interactions and reactions. And really a lot of what I'm talking about here is really trying to bridge this gap to chemistry using sort of traditional cold atom tools to really understand fundamental chemical interactions and bridge this gap between physics and chemistry that we put this arbitrary divide on. So I'm really interested in these sorts of molecules, but why cold? Why do we want to get these things cold? It's sort of the exact opposite of the talk that we just heard, in fact. So there's sort of many reasons we want to get these things cold. One is simplicity. Molecules are complex. And if we really want to study things, we want to study them sort of one single quantum state at a time. So if we can get them cold, we can create a single rotational and vibrational state and study these as a function of individual quantum states. So it helps us to make it a little simpler. Also, in terms of precisely measuring things, if we can get these cold, we can easily trap them. And as you know, the longer you can study something, the more precisely you can understand it, right? So if these things are zinging around in your vacuum system and you have a microsecond to look at them, the precision is going to be limited compared to if you could hold them for an hour in a trap. And then finally, this idea of control, where if you can get them cold enough, laboratory electric and magnetic fields and optical fields can actually exert significant forces on our molecules so that you can control the collision energy, orientation, and internal state. So it's these general ideas of really why we want to have these gas phase molecules really cold so we can able to understand some fundamental interactions. So I would say in general, the field of cold quantum chemistry is trying to answer some big questions, right? Can we understand how at a fundamental level, how a bond is broken or formed? You might think, oh, chemists have long since understood this, but really not on a very detailed level. And that's one of the things we're trying to explore. And also, if we have that knowledge, can we then control the reaction process? Can we drive the reactions along one pathway or another? And so these are some of the big questions that folks are trying to answer in this field. But I bet a lot of you are thinking, oh, wait a second. I remember from my first chemistry class, when we get to cold temperatures, chemistry stops, right? So if you look at this like simple diagram, right, as energy as a function of the reaction, say you have two diatomic molecules and they want to form a triatomic in an atom, and that's in lower energy. However, often these sort of reactions have a barrier and activation energy. So in the intermediate state, they have this sort of barrier. And of course, as you get to lower and lower temperatures, that barrier is going to suppress that reaction rate. And so at very low temperatures, no reactions occur. So isn't this an incredibly boring field to work in? Well, there's a trick. And that is that many ions and radicals are known to be barrierless. So it's downhill all the way. They may have a little barrier that's below the entrance channel here, but ultimately there's no barrier that they have to overcome. So these things continue to react even at very cold temperatures. So a lot of what we'll be talking about is actually reactions with ions and free radicals. And as I said, okay, so we want to study these ions and radicals, and we want to exhibit the sort of quantum behavior. So we want to be in single vibrational states. So if we think about what sort of molecules we want to study, well, if you look at some molecule like this molecule I took advantage of this morning, as it is very early here in Colorado. This is caffeine. And if you think about this, even at cold temperatures, there's many floppy, low energy vibrations. It's very hard to cool down to a single vibrational state. But if you have somewhat smaller molecules with less sort of floppy vibrations, these strong bonds, you can get big energy gaps to excite a vibration. And therefore, you can get in a very low vibrational, a single vibrational state in a molecule such as this. So, we really want to study these sort of small molecules if we want to sort of explore this sort of interesting quantum behavior at these cold temperatures. So if we think about studying cold quantum chemistry, really what we want to do is study small molecules. And of course, small is very relative in terms of what community you are in. For many of my chemist friends, this caffeine is way too small for them to care about. But we also want to look at radicals and ions. So is there any system out there where this is really relevant? And this goes so nicely into the previous talk, where we're looking at really molecular formation in the interstellar medium. Right, there have been many different molecules and ions detected. This is pretty old graph now of all the ones that have been detected. The blue ones are the cation species. And really understanding how we go from, from atoms to molecules to larger complex things is really, some of these processes are really not known, and the modeling is based on some simple approximations. So we really want to try to study these ion radical reactions, which are important in the interstellar medium. And in particular, we are interested in carbocations. So what is that? Well, it's just a molecule where you have the charge center on a carbon. Here's a nice molecule here. And these molecules have been detected in many environments, including Cassini has identified these carbocations in Titan's atmosphere. And so a lot of what we want to study is how we get from these small molecules to much larger molecules, starting from these, going to things like polycitric aromatic hydrocarbons, possible carriers of diffuse interstellar bands, and how those grow and grow until we get to aerosols. And so how do we start this chain? So we're really studying sort of the beginnings of this possible carbon chain growth. And so a lot of the work we're doing is with these small carbocations. Okay, so today I'd just like to tell you three sort of brief things. One, a little bit about our extreme environment for chemistry. It's not a beaker, it's a little bit of an unusual system. And I think it's sort of fun, and I'm always interested to hear what people have ideas to do in this environment. And then I'll first start off with a physicist reaction, which is a quantum state controlled reaction of calcium with a radical NO, and then move on to a little bit more real chemistry, where we're looking at carbon chloride plus with acetonitrile and seeing how we can explore these more complex reactions in our system. So all of our molecule reactions happen right here. So this is peering in through our vacuum system at our ion trap. It's a very, very simple system. You see some shiny electrodes that create electrodynamic trap for our ions. And then up here at the top, you see a microscope objective that can look in and image the fluorescence from our ions. And then the top of this base plate here is a time of flight mass spectrometer. So we can eventually determine the charge and mass ratio of all the ions in our trap. So our ions also are laser cooled. So we have some lasers that come in here. And when we have the cooling on, this in particular atom is calcium, we form something like a pseudocrystal called a Coulomb crystal. So each one of these little bright spots is imaging a location of a calcium ion. So this is a pure calcium crystal. Often we don't really care about the calcium itself. It's just a nice cold bath that we can dope in some interesting molecular products. And when we put those in, they displace the calcium, but they don't interact with the lasers. So you can see this dark core forming in this Coulomb crystal. These happen to be acetylene cations, but the idea is that they are being cooled sympathetically via the Coulomb interaction with our laser cooled calcium. So that's how we get our cold molecular ions. So it's important to know a little bit about how we laser cool ions, because that's going to impact how we control the quantum states. So it's a very simple energy structure for calcium, which is nice, partly why we like it so much. It has 3 relevant electronic states that we can address with 2 lasers. So we shine in a diode laser at 397 nanometers, and we scatter a bunch of photons to cool down our calcium. And most of the time, that atom falls back down to the S state. Occasionally, it falls back down to the D state, and we must move that atom back into the cooling cycle so we have a second laser. And so we basically just shine these 2 lasers in, and this thing cools down to millikelvin temperatures very readily. It's one of my favorite atoms. So we cool these, but we have to detect them. There are various ways we do that in our system. One is through the fluorescence, right? These are laser cooling. They're scattering photons all the time. And that microscope objective goes in and collects that fluorescence. And we have various different sizes of crystal. Over here, we have maybe about 1,500 calcium ions. We can go down to a beautiful string of them and down to a single trapped ion. But you can notice here, there's a little gap between 2 bright fluorescing ions in this string picture. There's clearly an ion there that's displacing the calcium, but it's not interacting with the laser. And so this is a problem. We can't just use fluorescence to detect our ions if we have molecules, because they don't interact with the laser. So in addition to sort of imaging of the ions, we also use time of flight mass spectrometry. And so it's basically, we have our trap here that we turn off, and we apply high voltages that accelerate our ions from the trap down to an ion detector. And then we look at the arrival time of those ions. So this is the ion signal as a function of time, or in this case, mass to charge ratio, and we can identify the different species. This is one of, I'm still sort of an atomic physicist at heart. So one of the first things we did is we put in every possible atom we could find around our institute and took a spectrum of that. You can kind of zoom in on my absolute favorite atom, my neutral atom, which is rubidium. And you can see we can distinguish between rubidium 87 and 85 very well. This is going to become important when we start studying chemistry, when we want to pluck off a hydrogen and put on a deuterium, to tag that and be able to distinguish the difference. Most of the data I will show you today actually comes from these time of flight traces, where we can determine the number of ions at each mass. Okay, so that's our system for for where we're going to study chemistry. So I want to sort of ease you into chemistry with sort of a physicist reaction where we're controlling the quantum state of the atom and therefore the reaction. So the reaction I want to talk about is NO. It's basically one of the few radicals you can buy in a bottle. It's quite corrosive, but you can buy it in a bottle, so that's nice. We may be sort of physical chemists, but we are definitely not synthetic chemists. And we want to react that with calcium. So why is that? Well, let's look at the energy structure down here. So here you see those three states of the calcium again. And then we can calculate the energy of a couple of reactions. One is a charge transfer here where we have NO plus and calcium. And the other one is where we have calcium oxide plus nitrogen. As you can see, these energies, this is about 3 eV higher in energy than the ground state of calcium. So honestly, nothing's going to happen here. This is one of those things that has a barrier, right, that we can't surmount. If you put these in, you have your calcium in the S1 state, nothing happens. It just sort of sits there. However, remember we have the laser cooling on, and sometime that atom is up here in this P state, right? Some fraction of the time it's up there. And now it has enough energy to react. And so we can see that depending on the amount of time that we can put the calcium up in this excited electronic state, that can control whether or not this reacts. So when it's up in the P state, we get a reaction. In the S state, no reaction. And so this is the idea of how we're going to control the reaction rate by the quantum state of the atom. So I promised individual ion reactions. And so here is a short movie of this reaction with calcium. You can see here, this is a calcium 44, which also doesn't interact with our lasers. And we're going to put a little bit of NO into our vacuum system so it reacts. In real time, this took an hour. We're much sped up. And so what I'm going to show you is the calcium, when they react, they're still going to be trapped in either the NO plus or the calcium oxide plus, but they're not going to interact with the laser. So you're going to see the blink out, but still remain in the trap and pushing ions around. So let's take a look at this. Yep, every time one blinks out, that is a reaction happening. And it progresses, these things sort of swap positions until we get to 3. After an hour, my students say, can we please stop taking this movie for your talk? I'm like, yes, this is all good. It took an hour to do just these few reactions because we have so few ions. This is not typically how we do reactions. In fact, we load this large crystal of ions so we can increase our statistics. So here is calcium reacting with NO, and there are 2 things you're going to see. One is you're going to see a dark core forming in the middle. All of those ions that are going to be formed in the center are going to be lighter than calcium. And anything that forms on the outside is going to be heavier than calcium and is going to form and flatten the crystal. The reason these have different locations within our trap is the strength of the trap depends on the mass. And so the lighter ions have a stronger potential and are forced towards the center. So if I start this by having the NO, you can immediately see sort of a dark core forming at the center here. Those ions are lighter than calcium and displacing calcium. And you can see it's getting very flat on the outside. There are ions out there forcing the calcium in. I always like to show this because this is the only time in my career where this is the first time we tried to do a reaction and it worked. How many experimentalists out there, the first time you try to do an experiment, it works? Like this never, ever happens. So I always love to show this as the very first reaction we ever did. But of course, there's not much we can tell besides it being lighter or heavier than calcium. So I will claim that this is NO plus and this is calcium oxide plus. But ultimately, you shouldn't trust me until we can look at the mass. So when we're done with the reaction, we put all of our ions into the time of flight mass spectrometer, and we get something like this. So this is our ion signal as a function of mass, and we can easily pick out our NO plus, calcium, and calcium oxide. And so we can integrate the area under these curves to get the actual number of these individual ions. And then we can look at this as a function of time. So here we have the normalized ion number as a function of reaction time. So notice this is 5 to 6 minutes of reaction. These are slow reactions. You can see the growth of NO plus here and calcium oxide. And as we proceed, you can see the calcium react away and we form these products. These red curves are fits to pseudo first order rate models. You can see a little bit of a curve there, right? And we can extract out the reaction rates from these fits. Okay, but I promised you we were going to be able to control these reactions. And so if we go back to our calcium energy structure here, the amount of time that the calcium spends in this excited P1/2 state depends on the laser power and the wavelength and the intensity. And so by tuning these things, we can control the fraction of the time the ion spends in this upper state. So I really like to show this picture. One can calculate and like, yes, we should see a reduced reaction if they're not in the P state, but just seeing the video, you can see by eye, the reaction is faster. So here are time synchronized videos where in the left hand, we have the ion spending 15% of its time in that excited state, and over here only 5%. So we should see a factor of 3 faster reaction on the left. And so I'll start this and you can instantly see how by just changing this, in our case, the frequency of the laser that's exciting changes that state. You can see the reaction change. So instantly you can see, right, this dark core forming. You can see a little bit here, but it takes a while, a large amount of deformation of this crystal. So it's really, you can see the reaction happening faster, which I think is very exciting just by tweaking the frequency of our laser. We can do this for many different P-state population here. So we look at the reaction rate, how fast it goes as a function of that population. And you have these nice linear curves, which you can extract out things like rate constants and branching ratios and get all that sort of classical, awesome chemistry information out of this. So instead of changing the population, we just change the quantum state of the reaction. Okay, so that, I say, is the physicist reaction, which we had a lot of fun with. We've sort of moved on to doing a lot of what I call real chemistry with molecular ions and neutral molecules. So in particular, some of the things that we want to look at are carbon chloride chemistry. So ion molecule reactions, right, they're really critical to understanding of sort of astrochemistry and the interstellar medium. Reactions, it's so rarefied gas that it's so rare for two things to come together that you better have a very strong probability of reacting for it to matter. And ions are one of those things, as well as radicals. Additionally, we know that chlorine is actually found in many molecules in space, right? H2 dominates everything, but these various chlorine-containing compounds have been found in space. And we know that carbon plus exists. And so reactions of this type will lead to CCl plus type ions. Until recently, we didn't have spectroscopy in the lab that was precise enough to go look for CCl plus. Just last year, Stefan Schlemmer's group in Cologne did some nice spectroscopy where now we have very precise spectroscopy. So I'm hoping the astrochemists will go and look for our CCl plus in space. So one of the hypotheses that we were trying to explore is, could CCl plus be the initiator for some possible carbon chain growth to make bigger and bigger and bigger carbon containing compounds in the interstellar medium? So you might think this might be a little bit silly because the literature really measured many compounds with CCl plus, and it doesn't react with a slew of these sorts of things. It's really non-reactive. So maybe this is not the best candidate to look for. Of course, the spoiler is, right, I wouldn't be telling you about this if we didn't see reactions. In fact, pretty much everything we try to react CCl plus with reacts beautifully, and we have all sorts of interesting things we're finding from it. So, why hasn't CCl been studied much in the lab before? Here is our first mass spectrum of trying to make CCl plus. So this is ion signal as a function of mass, right? There is CCl plus in there, but it's kind of a soup of ions, right? You create all of these things. It's very messy. And if we want to study just CCl plus, we just want to have that in our trap and not all of these other compounds. However, the trap allows us to purify the reactants. That's the sort of power of having this environment. So if we sort of zoom back out and look at that mass spectrum, here's our two isotopologues of CCl plus, but oh, there's other things in here. We just don't want those around. Remember before how I said every mass has a different trapping strength? That means it has a different trapping frequency. And so what we can go in do is shake our trap at the frequency that corresponds to a mass down here. We shake it, we add a bunch of energy, it just boils out of our trap, but leaves the other ones relatively untouched. So we can go through sweep and essentially clean out our trap so we have a very pure sample of our one isotopologue only of CCl plus. So that's sort of a fun bit we can do with our trap, where here's a picture. CCl plus is a sort of flat part out here, and then we have our nice calcium. And there's nothing else in there. So that allows us to study some peculiar ions that aren't possible in other types of apparatus. So the one reaction I want to tell you about today is CCl plus with acetonitrile. So that is CH3CN. So we've got our little methyl group right here, and then our CN, right? So this is a sort of interesting astrophysical molecule as well. And there's a couple of reasons why I want to show you this. So how we study this is by measuring these reaction curves. They get a little bit more complex now when you get to these molecules. This blue curve is our CCl plus reacting away. So it's decreasing over time, over about 6 minutes. And then we see two different masses pop up, and we can identify those as this black curve as protonated acetylene. That looks like down here. And then this green curve is this molecule C2, sorry, I messed up with this H, this is the black, this is the green, but regardless, they look the same in terms of they grow, but then they react away. They are lost from our trap. And the reason is because they're reacting again to form all of protonated acetonitrile. So in the end, all of our molecules that were started off as CCl plus end up as protonated acetonitrile ions. So what's going on here? So we can really distinguish these two different pathways. So if we look at our data, we have this model where we have, here's our carbon chloride ion. It's going to react with acetonitrile and produce these two intermediate products. However, they're hanging out in our trap and they see more acetonitrile. And so they're going to react and they form the exact same product. So we can see these two different pathways leading to a single product. And that's because sort of the sensitivity and the time scale that we can study these different reactions. So that's sort of fun in terms of understanding the mechanisms of what's going on. We're much more about mechanisms than rates, but they do tell us something. So if we look at 4 possible reactions, the first one is just CCl plus, or the lightest version of this, but we can look at the either isotopologue, the 37 isotope of chlorine, or luckily we can buy deuterated acetonitrile, right? Love buying things in a bottle. That's just wonderful for us. And so we can do all 4 possible reactions to look at how does this change when we change the mass of the individual atoms in our molecules. And so these are rate constants. That doesn't mean a whole lot to you, but let's compare to a few things. First, looking at the lightest species here, this is our sort of typical reaction with 35 and CH3CN. Well, what does that number mean? Well, we can compare this to very simple capture theories that say, basically, if these molecules get close, and we can define what close means, they're going to react with 100% probability. And that gives a remarkable agreement. And what that's telling us is that when these things get close and react, they react to products and don't pop back out into reactants. So everything proceeds to products. So that's what it's telling us. These things are reacting basically anytime they get close enough. And then there's something really unusual. As we get heavier and heavier, the rate increases. Now, this may very likely be some sort of uncontrolled systematic in our experiment that we're looking for. So, don't hold me to this. I'm curious what this is. We don't know. But could there be an inverse kinetic isotope effect? This has inverse kinetic isotopes have been seen in various systems. Our system doesn't quite have the characteristics that would lead to this, but it's sort of an interesting thing that we're trying to explore. It gets faster as things get heavier, where normally you think the opposite. All right, so takeaways from this. So ion trapping, right, can allow us to study these ion molecule reactions at cold temperatures and really be able to control the interactions, which can lead to a lot of new interesting things. And we can really start probing these reactions that really weren't possible in the lab before because of this capability. So the spectacular team that worked on all of this, Tommy Garcia, Caroline Preitzel, Trevor Keefe, Chase Zagoric Marks, and most of the reactions I showed you today were from Olivia Krohn. And I would be remiss if I don't take this opportunity to say, hey, I've got postdoc positions available. See this little arrow? This is our lab. Isn't this a gorgeous place to live and work? Come to Boulder. You don't have to have done things like this before. Come and explore a new field and enjoy the intersection between chemistry and physics. Thank you.
Thank you very much for this really inspiring and interesting talk. Please, everyone, post your questions in the Q&A part. There was a question by Tamara, who's asking, why is there no activation energy or barrier for the ion radicals? So where does the lower hill come from? That you pointed out in the beginning.
Yeah, so sometimes there are we still have intermediate states where these things come together and isomerize, and those can have energies that are lower than the lowest energy. Look at this. Move my chat over here. So yeah, this is the actual total potential energy space for this. And so if these things come together, there can be transition states where they form these sort of transition states. These aren't stable intermediate products, but they have a higher energy than the final products out here. And so you can get all these things which are called submerged barriers. They're submerged below the top energy, but it happens to do the dynamics of the isomerization and the reaction paths.
Another question just regarding your answer. Thanks in the first place. What does this, like, how do you calculate this energy? What does it measure exactly?
Right. So these energies for the experts are used at the CCSD-T level, complete basis set. So we use both DFT and CCSD to sort of calculate these energies. These are sort of stable. These are the intermediate states, so they're stable energies. A transition state here means it has one imaginary frequency. In other words, it's sort of on a metastable state. It will fall down to one of these things. And so these are the difference between these sort of transition states versus the intermediate.
All right, thanks.
Maybe a related question, since there's no other question. Is there some chance to kind of do some time resolved measurements to understand kind of this dynamic happening, or what is actually, you can make energetic arguments, but can you also see how the reaction is actually happening?
Right. So if you wanted to sort of probe a transition state, so this whole thing happens very, very fast. So you would need, to look, so there's a lot of sort of ultra fast, femtosecond experiments that try to probe these transition states. And that's sort of one of the really frontiers of understand to be able to measure these transition states and follow this through. For our apparatus, we are definitely on a slower time scale, and so we are just looking at the final products, in fact.
Okay. Are there any other questions? Let's talk from the audience or from the panel. Maybe I can ask one other question, since we had you mentioned this relevance of these molecules to astrophysics. So can your science tell your astrophysics colleagues something about, say, the nebula or the different, the composition of these elements in space?
Yeah, I mean, our hope is that by modeling these reactions, both understanding the mechanisms and the rates, that those can go into the way folks are modeling the interstellar median and things like that. So hopefully these can be inputs to their models. Often they use this sort of very simple capture, cross-section, Langevin type theory to sort of model these things. If we can be able to measure more precisely these rates, that will help them more precisely measure and accurately measure or predict how these systems are evolving.
I see. Okay. So